Hello, welcome to another module in this massive open online course on probability and random variables for wireless communication. So, in the previous modules we have looked at Gaussian random variables and properties of Gaussian random variables, and especially the linear combination of Gaussian random variables which results in another Gaussian random variable. Let us look today at an application, at a novel application of this property of Gaussian random variables from wireless communication in the context of antenna arrays or array processing or also beamforming. Okay. So, let us look at an application of our Gaussian random variables in the context of antenna, in the context of antenna arrays or array processing, right. So, what are we considering? Let us again, let me draw a schematic. Let me consider a receiver with multiple antennas. So, what I am drawing here is I am drawing a wireless receiver with multiple antennas here, okay, such that the spacing between antennas. So, these antennas are arranged in a line or these antennas are arranged linearly such that the spacing between antennas, so the spacing between antennas is constant, spacing between antennas is equal to d. So, this is a linear array of antennas, in the sense antennas are arranged in a line in a linear fashion, and the spacing between two antennas, that is the spacing between adjacent antennas is t, that is each antenna is spaced distance, that is each antenna is spaced at length d from the next antenna. So, the spacing between these antennas is uniform, and this is an array of antennas, this is known as a uniform linear array. So, this such a spacing of antennas, such an antenna configuration, this is known as a uniform linear array, and in this uniform linear array let us consider which a signal which is arriving at an angle of. So, we have a signal which is arriving at an angle of theta, this angle theta, this is known as the angle, of arrival. So, I am considering an antenna array, a uniform linear array with antenna spacing d and a signal which is arriving at an angle of theta with the vertical, this is known as the angle of arrival of the signal. Okay. And let yi denote the signal at the ith antenna. Okay. So, which means y1 is the signal at the first antenna, y2 is the signal at the second antenna, so on if we have L antennas. So, we are considering a scenario with L, antennas, which implies that YL is the signal at the Lth antenna. So, what I am saying is Yi is the signal received at the yi is the signal received at the ith antenna, and the spacing between the antennas is d, theta is the angle of arrival. This is known as the uniform linear array with antenna spacing d. There are L antennas, okay, and yi is the signal received at the ith antenna. Therefore, we have signals y1, y2, yl which are received at the L antennas in this uniform linear array architecture. Now, let us write the system model for this uniform linear array. So, the system model for this uniform linear array is given as follows. So, the system model is given as follows. The system model so the system model for this uniform linear array is given as the signal yi received at the ith antenna is given as the transmitted signal x times e to the power of minus I minus 1 phi times x times e to the power of minus I minus 1 phi plus wi, where wi is the Gaussian noise. This is Gaussian noise. Therefore, now let us substitute the different values of I, that is I equals 1 comma 2 so on up to L. Therefore, I have y 1 equals e to the power of minus I minus 1, that is when I equal to 1 this is 1, y 1 equals x plus w 1, y 2 equals x times e to the power of minus j phi plus w 2, y 3 equals x times e to the power of minus j 2 phi plus w 3, so on and so forth. I have y l equals x e to the power of minus j l minus 1 phi plus w l. Okay, this is the system model, right. We are saying the signal of yi received at the ith antenna is yi equals x, that is the transmitted signal, times e to the power of minus j I minus 1 phi plus w I. Okay. And therefore, now you can see I have y 1 equals x plus w 1, y 2 equals x e to the power of minus j phi plus w 2, y 3 equals x e to the power of minus j 2 phi plus w 3. Therefore, each the received signal, that is if you remove the noise, that is you see that the received signal at the first antenna is x e to the x, at the second antenna it is x e to the power of minus j phi, at the third antenna it is x e to the power of minus j 2 phi. So, the signal at each successive receive antenna is delayed by a phase factor e to the power of minus j phi corresponding to the signal at the previous receive antenna, right. So, we have the signal at the first antenna which is x, second antenna x into e to the power of minus j phi, third antenna x into e to the power of minus j 2 phi. So, this signal at each successive receive antenna is delayed by, has an additional phase factor of e to the power of minus j phi. Therefore, this is also known as a phased antenna array, there is a phased array, alright. So, this uniform linear array, because each successive, the signal at each successive antenna has a phase with respect to the signal at the previous antenna, this is known as a phased antenna array, or this is simply known as a phased array. So, this concept, this is known as a phased array of antenna. So, this is known as a phased this is known as a phased array, and signal at each successive antenna has a phase difference of e to the power of minus j phi with respect to the previous antenna. has a phase difference of e to the power of minus j phi with respect to the previous antenna. Therefore, this is also known as a phased array or a phased antenna array. Okay. So, now let us look at signal processing for this phased antenna array. How do we process the received signals y1, y2, yl in this phased array or in this uniform linear array? So, I have the signals. Now, before I write the system model, let me describe to you what this angle phi is. This phi is related to the angle of arrival theta as phi equals 2 pi fc d cosine theta divided by c. Now, c over fc is lambda, which is the wavelength. So, this phi is also 2 pi. So, let me write this a little clearly. This phi is equal to 2 pi d divided by lambda cosine theta, where you probably remember that this theta is the angle of arrival, or theta is the angle between the signal and the vertical line, that is, this is theta is also known as the angle of arrival for this uniform linear array or for this phased array. Okay. Now, let us look at signal processing for this phased array. The system model, the vector system model for this phased array, that is given as y1, y2, yl. This vector is equal to, I have 1 e to the power of minus j phi, e to the power of minus j 2 phi, so on e to the power of minus j l minus 1 phi times x plus w1, w2, so on up to wl. So, this I can denote by my received vector y bar. This I can call it as the vector h bar phi, which depends on the angle phi, and this I can call it as basically my noise vector w bar, and this also I can write this h bar as a function of theta also. I am writing it here as a phi function of phi. This is known as the array steering vector, alright. So, this h bar, which is a function of this vector h bar, which is a function of phi, but remember phi is a function of the angle of arrival theta. So, each different angle of arrival theta corresponds to a different vector h bar. So, this h bar of phi is also known as the array steering vector. It is as if you are steering the array in the direction of theta, that is the direction of the angle of arrival theta. So, I can write this system model, that is a received signal vector y bar consisting of y1, y2, yl, where yi is the signal received at the ith antenna, y bar equals h bar phi times x, which is the transmitted signal, plus w bar, which is the noise vector, where h bar phi, where phi is in fact a function of the angle of arrival theta. This is known as the array steering. This is known as the array steering vector. I have expressed this system model in terms of the array steering vector. Okay. Now, let us write the system model. Now, let us look at the signal processing. So, I have y bar equals h bar of phi times x plus w bar, where h bar phi is the array steering vector. Further, now let us look at the properties of noise as seen in the special case in previous module, as seen in previous module. Consider W1, W2, WL, consider these noise samples W1, W2, WL to be IID Gaussian, that is independent identically distributed Gaussian. Remember what is IID? That is independent identically distributed identically distributed Gaussian with 0 mean, that is each Gaussian random variable, each noise sample Wi has mean equal to 0. Further, let us assume that each noise sample has power or variance expected magnitude Wi square equals sigma square. So, this is basically your 0 mean, this is the variance or noise power. Further, we also assumed that the noise samples are unindependent, that is they are uncorrelated. Expected value of, since this is complex noise, I am writing Wi Wj conjugate is equal to 0, which means noise samples, different noise samples, the different noise samples on different antennas are uncorrelated. These noise samples are basically independent, which also automatically means they are uncorrelated. However, remember only in the case of Gaussian, uncorrelated also means that they are independent. So, we are considering independent identically distributed Gaussian noise samples with 0 mean, variance sigma square, and covariance between the noise samples at two different antennas is equal to 0. Okay. Now, let us consider combining of the received samples y1, y2 up to yl. So, what I am going to do now, I have consider the combiner or what is also known as the beamformer A bar equals A1, A2 so on up to AL. This is a vector of size L, this is A bar equals A1, A2, AL, and now I am going to form y tilde equals, well, y tilde equals A1 conjugate y1 plus A2 conjugate y2 plus AL conjugate YL, which I can write as A1 conjugate, A2 conjugate so on AL conjugate times y1, y2 up to yl. And now you can see this is basically nothing but my vector A bar Hermitian. This is my vector A bar Hermitian, this is my vector y bar. So, this is A bar Hermitian times y bar. So, I am forming. So, what I am doing are combining these received samples y1, y2, yl using the weights A1, A2, AL. I am performing A1 conjugate y1 plus A2 conjugate y2 so on AL conjugate yl, which I can write as the vector A bar Hermitian times y bar. This combining vector, this vector of combination A bar, this is also known as a beamformer, and this process is also known as beamforming. So, this vector, this combining vector A bar, this is also known as a beamformer, and this process is also known as the, this process is also termed as beamforming. So, now I have y tilde, I have basically y tilde equals A bar Hermitian, y tilde equals A bar Hermitian y bar, which is equal to, remember y bar is the array steering vector h bar phi times x plus w bar, which is equal to A bar Hermitian H bar phi times x plus A bar Hermitian times W bar. This, remember, this is the signal part, this is the signal part, this is the noise, this is the noise part. In addition, let us say that the transmitted signal power is P, that is expected value of magnitude x square. Remember, the power in the transmitted signal is the nothing but the variance of the signal, expected value of magnitude x square equals P. Let us assume that the transmitted signal, power is P. Let us now look at what is the signal to noise power ratio of this system, alright. So, we are looking at a beamformer, we are looking at performing A bar Hermitian times y bar. We have isolated the signal part, we have isolated the noise part. Let us now look at the signal to noise power ratio, which is the power in the signal to the power in the noise. So, let us now look at the signal to noise power ratio SNR, which is equal to the ratio of the signal power to the noise power, which is equal to magnitude of A bar Hermitian H bar phi magnitude square expected magnitude x square divided by the noise power. This is the signal power, is magnitude of A bar Hermitian H bar phi magnitude square times expected magnitude x square, which is P, divided by the noise power. Okay. Now, let us look at what is the noise power of this system. Now, previously we have seen, and this is where our properties of Gaussian will come handy. Remember, the noise power, remember the noise is A bar Hermitian W bar, that is a linear combination of Gaussian random variables. Previously we have seen, and we have seen previously we have seen that if W1, W2, WL are Gaussian, and in fact if they are IID Gaussian with 0 mean, we have A bar Hermitian W bar that is we are performing a linear combination of Gaussian noise samples, W1, W2 up to WL are Gaussian. Therefore, when we combine them with the coefficients A1, A2, AL, the resulting noise, that is A bar Hermitian W bar, that is Gaussian in nature. Further, if each of these samples W1, W2, WL is 0 mean, then the resulting noise, that is A bar Hermitian W bar, is also 0 mean. So, expected value of A bar Hermitian W bar, this is equal to 0. So, this basically this is 0, this is 0 mean noise. Further, the noise variance or the resulting noise power, that is magnitude of A bar Hermitian W bar, this is equal to sigma square times norm of A bar square. We had seen this also in the previous module, that is when we perform A bar Hermitian, or we had seen previously in the context of real vectors, we had seen A bar transpose W bar. Now, this is a complex vector. So, we are considering A bar Hermitian W bar, we are saying the noise is 0 mean, and the variance of noise, since all the noise samples are identical, that is have identical variance sigma square, the variance of the noise at output is sigma square times norm of A bar square. Therefore, the SNR becomes SNR. Remember, previously we had said SNR equals magnitude A bar Hermitian h bar phi whole square times expected magnitude x square, that is signal power, that is P, divided by the noise power, which is sigma square norm of A bar square. Therefore, my SNR becomes magnitude A bar Hermitian h bar phi, is array steering vector, square P, which is the transmitted signal power, divided by the noise power, that is sigma square times norm of sigma square times the norm of A bar square. Therefore, this is the expression. Now, this is the expression for a general beamformer A. This is the expression that we derive for the SNR at the, this is the expression that we derive for the SNR at the output. Now, we want to find the signal, now we want to find the beamforming vector A bar or the beamforming weights A1, A2, AL, which will maximize the SNR at the output of this uniform linear array or this phased array. That is, we want to find the beamformer A bar which will yield the maximum SNR, so that we enhance the signal to noise power ratio at the output. So, we want to find A bar which maximizes SNR, at the output. Now, you can see from this expression, from the Cauchy-Schwarz inequality, I have magnitude A bar Hermitian h bar phi whole square less than or equal to norm of A bar square times norm of h bar phi whole square. I have this follows from what is known as the Cauchy-Schwarz, also sometimes known simply as the Schwarz inequality. This follows from the Cauchy-Schwarz inequality, that the magnitude of A bar Hermitian h bar phi magnitude square is less than or equal to norm A bar square times norm of h bar phi square. Therefore, my SNR is less than or equal to magnitude A bar square magnitude h bar phi whole square times P divided by the noise power, which is sigma square norm A bar square, the norm A bar square in the numerator and the norm A bar square in the denominator, these cancel. Therefore, the maximum SNR is given as norm h bar phi whole square P divided by sigma square. Remember, this is the maximum SNR. Maximum SNR is norm of h bar phi square P divided by sigma square. This is what we derive from the Cauchy-Schwarz inequality. And now, let us see what is this maximum SNR. Now, maximum SNR, remember maximum SNR, now h bar of phi is, remember, 1 e power minus j phi, so on e power minus j L minus 1 phi. Therefore, the maximum SNR, so norm of h bar phi whole square, norm of h bar phi whole square is 1 plus magnitude e power minus j phi whole square plus magnitude e power minus j 2 phi whole square plus so on magnitude e power minus j L minus 1 phi whole square, all of these are phase factors. So, magnitude square is 1, which is basically 1 plus 1 plus 1 L times, this is the sum of 1 which is taken L times, and this is equal to L. So, norm of h bar phi whole square equals n. Therefore, the maximum SNR, is given as L times P divided by sigma square, and this factor of L in this system provided this by this array is also known as the array gain of this system. So, what are we seeing? We are seeing something very interesting. We are seeing the maximum SNR is given as norm of h bar phi whole square times P divided by sigma square, but norm of h bar phi square we have seen is L. So, the SNR at the output of the beamformer is L times P over sigma square. Remember, without the array, the initial signal to noise power ratio is simply P over sigma square. So, using this phased array, using this uniform linear array, we are able to multiply this signal to noise power ratio by a factor of L. So, this factor of L, where L is the number of antennas, this factor of L gain in the signal to noise power ratio at the output of this uniform linear array, this is known as the array gain. So, we are able to multiply the initial SNR by the factor of L, this is known as the array gain of the system, and therefore, the uniform linear array is a very important or is a very novel technology, because it results in a gain of a factor of L in the signal to noise power ratio at the receiver. So, what do we have? We have the SNR of the phased array, that is SNR of the uniform linear array equals L times initial SNR. What do I mean by the initial SNR? That is, initial SNR is P by sigma square, that is without the signal array, without the phased array. Therefore, this we have a gain of L, and this is the array gain. This is the array gain of the system. Now, how do we choose the combining weights A1, A2, AL? Remember, for the Cauchy-Schwarz inequality, if we look at the Cauchy-Schwarz inequality, we have A bar Hermitian h bar phi magnitude square is less than or equal to norm A bar square into norm h bar phi square. Equality occurs only when A bar, that is the combining vector, is proportional to the vector h bar. Equality occurs when A bar is proportional to h bar. So, here equality occurs when A bar is proportional to h bar of phi, and one way to achieve this Cauchy-Schwarz inequality therefore is to set A bar simply equal to h bar phi. Therefore, we can choose A bar simply equal to h bar phi, and therefore, if we choose A bar is equal to h bar phi for maximum SNR, choose A bar equals h bar phi, which is basically 1 e to the power of minus j phi, e to the power of minus j 2 phi, e to the power of minus j L minus 1 phi, which is basically simply your h bar phi. Therefore, now the optimal beamformer will be given as, optimal combining will be given as y tilde is equal to A1 conjugate times y1 plus A2 conjugate times y2 plus so on AL conjugate times YL which is equal to 1 times y1, which is y1, plus e to the power of j phi times y2, e to the power of j 2 phi times y3, plus e to the power of j l minus 1 phi times yl, and therefore, this is the optimal combiner. This basically, we remember this is equal to, this is also equal to a bar Hermitian times y bar, which is equal to a1 conjugate, a2 conjugate, so on up to al conjugate times y1, y2 up to yl, and that is equal to y1 plus e to the power of j phi times y2 plus e to the power of j 2 phi times y3, so on e to the power of j l minus 1 phi times yl. This is also known as this combiner, that is this optimal combiner, which results in the maximum SNR. Remember, what is the maximum SNR? L times P over sigma square. This is known as the maximal ratio combiner. Since it maximizes the ratio of the signal power to the noise power at the receiver, this optimal beamformer, which maximizes the SNR at the receiver, this is also known as the maximal ratio combiner for this array processing system, or this is also the matched filter. Remember, since A bar is equal to H bar, that is the filter, that is the receive filter, is matched to the array's tiering vector. This is also known as the spatially matched filter. This is also known as the matched filter, or this is also known as the maximal ratio combiner. So, this particular beamformer where A bar, which is equal to H bar of phi. So, this particular beamformer, that is A bar, this is equal to H bar of phi. This is also known as the maximal ratio combiner, MRC, or this is also known as the, this is known as the maximal ratio combiner, or this is also known as the matched, this is also known as the matched filter. Alright, so this is a unique application of this Gaussian and properties of Gaussian in the context of signal processing, in the context of wireless communication. What we have said, we have considered a multiple receive antenna set of L receive antennas with equal antenna spacing, that is in terms of a phased array. We have looked at a signal which is arriving at an angle of theta with respect to the vertical, that is angle of arrival theta. We have considered independent identically distributed noise elements at the different receive antennas, and we have demonstrated that using the maximal ratio combiner or using the optimal beamformer or the matched filter, one can enhance the signal to noise power ratio in this uniform linear array or phased array system by a factor of L, where L is the number of antennas. Therefore, this L is also known as the array gain of the system, and this is basically possible because of the coherent combining of the signals received across the various receive antennas. That is, remember, we are performing y1 plus e to the power of j phi times y2 plus e to the power of j 2 phi times y3, so on. That is, we are inverting the phase of the received signal on each antenna, combining them. That is, the signal combines coherently, whereas the noise, which is random, the Gaussian noise, combines incoherently. Therefore, we are able to enhance the signal to noise power ratio by a factor of L, and which is the array gain, and this is an important property. This is demonstrates an important application of both signal processing in wireless systems, and also the principle of combination of these Gaussian noise samples across the various receive antennas. So, with this, let us end this module here. We will look at other aspects in the subsequent modules. Thank you very much.